Now we'll talk about the correlation coefficient. When you've got two variables x and y, you can compute their correlation coefficient from a number of observations. To do this, we first put x and y in standard units. Remember, that means you take x and you subtract off the mean of x, the average of x, and then you divide your values by the standard deviation of x. That makes x a unitless variable, and we do the same thing to y. Now what we do is we imagine x and y as columns in a table, and think of those columns as column vectors. And we can take the dot product of those two vectors. That is, we multiply each x observation and each y observation, and then we add them all up. And then we divide by the total number of observations. So what we're saying is that the correlation coefficient can be computed by taking the average of the product of x in standard units and y in standard units. The correlation coefficient, which we call R, measures how clustered the scatter is around a straight line. It measures linear association and only linear association. It's based on standard units. And R always lies between -1 and 1. When R equals 1, the scatter is a perfect straight line that slopes upwards. When R is -1, the scatter is a perfect straight line sloping downwards. And when R is 0, there's no linear association. We say that the two variables are uncorrelated. That doesn't mean that there's no connection between the two variables, that there's no somehow trends there at all. It's just that there's no linear trend. So positive values of R correspond to positive association, and negative values of R correspond to negative association, but values of R that are very close to 1 or -1 indicate that we have data that lies very close to a straight line. Let's look at this in the demo. So we're going to convert some data to standard units and show that that doesn't change the trend. Here's a function that converts an array of numbers to standard units. We take that array, we subtract off the mean of the array from each number, and then we divide by the standard deviation, and then we return the resulting array. Let's compute the standard units for several columns in the hybrid table, and then plot the same scatter plots as we had above, these ones, right? This one with price versus mileage, and this one with price versus acceleration. But this time we'll plot them in standard units. Let's add some columns to our hybrid table to measure mileage and sticker price and acceleration in terms of standard units. Here we have them. And remember that a standard units of 0.59 like this means that the mileage per gallon for this car is slightly higher than the average. It's 0.6 standard deviations above the average. Here's a car that's 1.76 standard deviations above the average. Sometimes the prices might be lower than the average, and this one's about 0.6 standard deviations below the average for the prices. All right, let's look at the scatter plot of sticker price versus mileage. You see this graph, and let's compare that to this graph here, and I think you'll see that they're almost exactly the same graphs. The only thing that's changing are the labels here on the axes. Okay. So here's the same graph. All that's changing is the labels on the axes, and it's been centered slightly differently as well. Here we'll plot acceleration on the x-axis and sticker price on the y-axis. And again, we get exactly the same positive trend that we had before, um, um, but the axes have been relabeled. So the shape of the graphs doesn't change, just the labels on the axes. When you change to standard units, the trend or association is preserved. Correlation has an easy formula in terms of variables and standard units. And because of that, it's very helpful to convert to standard units when you're computing correlation. And that's why we always use standard units when talking about correlation. Okay, here's a nice function, correlation function, and it takes a table, T, and a label for the x variable and a label for the y variable. So these are the names of the x and y columns. And it will first transform x into standard units, then transform y into standard units, and then it will compute the average of the dot product, component-wise product of the x and y in standard units. And what we can see from the following code is that the correlation coefficient for a plot with negative association, like sticker price versus mileage, we see the negative association here. And when we compute the correlation coefficient, we see that it's also a negative number. It's minus 0.53. It's not that close to 1. This isn't really that close to a linear relationship, but it's definitely a negative association. And similarly, if you have a positive association, like the association between sticker price and acceleration, you can compute its correlation coefficient and find a positive number. Here we get a number that's maybe a little bit closer to 1.7, and that's because we do see some kind of trend here that looks maybe close to linear, but there's quite an awful lot of scatter off kind of line of best fit here, and so maybe we should be cautious about saying that there's a really strong linear association here, but there's definitely a positive trend, and that's measured by the positive R value.